Okay, before getting started the chapter 8 about the dynamics, I will review those exercise 7.1 and 3 and 4 because Kwang has asked to solve this problem. Okay, if you ask something, then let me add how to solve it in the video lecture. Okay, you can email me or you can add some comment to the class website. Okay, the problem is that find inverse kinematics, forward kinematics, and end effector singularity and the actual singularity. We should check this kind of singularity for given 3 RPR planar parallel mechanism. Okay, as you can see in this figure, we have the 3 leg. Okay, so maybe this vector can be denoted by the A1. A1 is obtained. The magnitude of the A in the minus x direction, there is no y, so 0 is added here. Okay, and this angle can be defined by the theta 1, 1. And for the given prismatic joint, the displacement will be denoted by the theta 1, 2. There is a translational quantity. The direction of the prismatic joint action is denoted by the n1 hat. And for given configuration, n1 hat is given by 0, 1 because it is aligned with the plus y direction. And we will add some prismatic, some translational, some position vector will be denoted by the p. Okay, for given body frame, denoted by here p. Okay, and then okay, the rotation matrix is given. Rotation angle. There is no notation about the orientation of body frame, but we will add pi to denote the angle. Okay, and then this vector will be denoted by the b1. Okay, so we can make the closed loop. Okay, for the IK problem is given by the statement of PR. P has the two quantity such as the px and py. Okay, because it is planar problem, and the rotation matrix has the four quantity, but 3 is dependent and the 1 is independent, such as the pi here. For given P and R, 3 is known, we should find out the theta 1, 2. Okay? And theta 2, 2. Theta 2, 2 will be this one. Okay? Theta 2, 2. Maybe this is the theta 3, 2. Okay? Theta 2, 2 and the theta 3, 2. We should find out the theta variable in this mechanism. Okay. Okay. It's not difficult. Let's make the closed loop, such as a vector plus theta 1, 2 and one direction will be equal to the p plus rotation matrix and the b1, because b1 is given by the body frame, so we should multiply the rotation matrix to denote all the vectors in the space frame. Okay, here this is the space frame. Okay, maybe you know this equation. It's not difficult. Okay, as you can see here, we know the A1, and we want to find out these values. Okay, the p and rotations and the b's, all the variable is given, so we know that. So we will denote this quantity as a v1. Okay, this is unknown. The remaining things are known variable here. Okay, so the theta 1, 2 can be obtained by using the p plus p1 minus a1 as a magnitude. If you wanted to make the scale value, then the transpose operator can be added to here as suggested in the textbook. Okay, like this we can find out the theta 1 variable. One more, maybe the second loop, this is the a2 plus theta 2 n2 as a unit vector will be equal to p plus rb2. Let's denote it as v2 because we know the every variable except the theta 2. So theta 2 can be obtained as a magnitude p plus rb2 minus a2. Okay. The third loop can be found out using the similar procedure, a3 plus, the theta 2 n3 and p plus rp3, okay, v3. So theta 3 can be found out using the magnitude p plus rp3 minus a3. Okay. So this is the procedure to solve the inverse kinematics of this mechanism. Okay. Okay. The forward kinematics are a little bit difficult compared to the inverse kinematics. So the forward kinematics is stated for given theta variable. Okay, we will find out the p and r, three unknown. Okay. Let's denote first equation as a 1. This is the 2. This is the 3. Okay. Equation 1, 2, 3 will be the two-dimensional vector equation. So let's subtract equation number 1 minus equation number 2. This will be v1 minus v2 p. Maybe the p is the same. If we subtract each other, then p will be removed in this equation. Okay, and then rotation matrix, and then b1 minus b2. Okay, 2 minus 3 will be the v2 minus v3. Will be the same rotation matrix because the computation is the same, b2 minus b3. Okay, let's collect this vector such as v1 minus v2 as a column vector, v2 minus v3. So this will be the 2 by 2 matrix, and then rotation matrix using the similar procedure, b1 minus b2 as a first column, b2 minus b3. So rotation matrix can be obtained using the inverse matrix. So okay, let's denote that this is the V matrix, this is the P matrix. At that time, V, P inverse will be the rotation matrix. So we find out what the rotation matrix is, and then the P vector, it's very easy. P vector is obtained Vi minus rotation matrix and Pi for I will be the 1, 2, 3. Anything, any value can be chosen to obtain the P. Like this, we can find out the rotation matrix and the position vector of a base frame, the body vector, body frame. Okay, so we have resolved the inverse kinematics and the forward kinematics for this configuration. Okay, the third problem is about the end-effector singularity. Okay, this is the end-effector. Okay, so let's take the Length notation to obtain the inverse matrix of the body Jacobian. Okay, see, the length will be the Jacobian inverse transpose and a linear torque, a linear vector, linear force here, because because the three-dimensional prismatic actuator will provide the linear force. So linear force will be denoted by the Fi using the tau I. Tau I is the magnitude, and implies the unit directional vector. Okay, so we will check this matrix. It is called as inverse matrix, inverse Jacobian of inverse matrix of body Jacobian. Okay, the length can be obtained easily. Just to consider the moment obtained at the body frame. Okay, here the length will be in the planar case. Length will be denoted by the mz, moment in the direction of the g, and fx and fy. This will be the planar length, and some Jacobian and the linear force tau 1, tau 2, and the tau 3. Okay, as you can see here. Okay, the moment g, mz, can be obtained using the b vector cross cross F1, okay, and B2 cross F2 plus B3 cross F3. But B is described in the body frame, so we want to unify the every notation in the space frame, fixed frame. So rotation matrix should be multiplied. Like this. The F vector will be according to the definition of the N1. This will be the 0, 1 and the tau 1. This will be the 0, minus 1, tau 2. And F3 will be the 0, 1 and tau 3. According to the definition of the linear pulse. Here the cross product will be applied to here in the vector. The first element will appear in the g direction according to the definition of the cross product. So RB1X will appear in the g direction. How about this one? How about this one? Maybe the first element will be denoted as a minus direction. So minus RB2X. The third one will be the, it's very small, so I will extend it. Rotation B3 x direction. Okay. How about the linear poles? Linear poles is the same. So 0, 1, 0, minus 1, 0, 1. So this will be the inverse matrix of the body Jacobian. Okay. Okay, it's not difficult. Okay, let's check the rank of this matrix. As mentioned before, this is the Jacobian minus inverse transpose. But the first column has some variable. Third column has some 1 or minus 1 element. But the second row will be the 0. So the rank will be J inverse transpose is the 2. It means singular. This computation is a singular. Actually, it depends on the end effector position. If you change the end effector, the end effector singularity can be removed or added. Okay, so this configuration must be the actuator singular. I'm sorry, the end effector singular configuration. Do you understand? If you have any questions, let me know that. I will reply when you ask something in the textbook. Okay. One more, we will find out the actuator singularity from this configuration. Okay. I will delete Is there a good way to delete? So I don't know what to do. So okay. It takes some time. Okay, let's check the actuator singularity for this computation of this mechanism. It's not difficult. Please follow the my procedure. It can be very helpful to how to drive kinematics of parallel mechanism. Okay, I've done. Okay, the last issue is about the actuator singularity. Okay, actuator singularity. In order to talk about the actuator singularity, we should find out this equation. Maybe you know that the twist will be first Jacobian and theta 1 dot. Theta 1 dot has the three elements, theta 1 1 and the theta 2 1, theta 1 2 and the theta 3 1 3. Like this, it must be the vector. It will be equal to J2 theta 2 dot, J3 theta 3 dot. By using the subtraction, J1 theta 1 dot minus J2 theta 2 dot must be 0. One more, J2 minus theta 2 dot plus J3 theta 3 dot is 0. By collecting these two equations, we can make the another Jacobian, such as J1 minus J2, 0, 3 times 3, 0, 3 times 3, and minus J2 plus J3. And theta 1 dot, maybe the 3 element, theta 2 dot has the 3, theta 3 dot. So the last column will be the 9 element, will be the 0, 6-dimensional 0 vector. Okay. it can be used to obtain the actuator singularity. Okay. Anyway, we will derive this equation. The first one will be the J1. Okay. Second, J2, and third, J3. Okay. Let's apply the screw axis for this computation. Okay. J1 will be, okay, the first, I'm sorry, it is the twist. Okay. Twist will be the J1 and theta 1 1 dot, theta 1 2 dot, theta 1 3 dot. Okay. This equation. Okay. The first column, actually this is about this linkage, is it right? We can consider as an open chain from the space frame to the body frame. Okay, so we will derive the Jacobian for this open chain. Okay, the first column is about the A1. Okay, here, okay, every twist will be obtained using the space frame. Okay. So this rotation velocity will be normalized using a 1. Is it right? And then A1 minus A1 cross omega g omega a m1 will be the first screw of this element. So okay, let's make the movement. If you make rotational motion that here, maybe this space frame will move this way using the magnitude of the A1. Is it right? In the y direction. So 0 and A1. This will be the first screw axis. Is it right? Okay, let's obtain the second screw axis. Okay, if you move, the theta 1, 2 is about the linear movement of this prismatic joint. So there is no rotation movement. It is corresponding to the y direction. So 0 and 1. In the case of the linear movement, the rotation part will be the 0, but linear part should be normalized. Okay. How about the third element? Okay, it is about the g-axis rotation. Maybe the omega 1, 3 as a 1. So 1 will be given. This rotation will make the some.
죄송합니다. 아무리 찾아봐도 가지고 계신 음악 중에서 텔리시한 오메가는 안 보이네요.
I'm sorry, my Siri is responding to my my talk. Okay, let's find out this linear velocity. It is corresponding to this axis movement and this axis movement. You right? In here, this angle or this linear displacement is corresponding to the theta 1, 2. Okay? So this value is the theta 1, 2. This is the A1 magnitude. So in the case of x direction, theta 1, 2 should be multiplied in the x direction. How about the y? In the case of the y direction, the magnitude of the A should be added in the square axis, so A1. Like this, we can find out the J1. Okay? Actually, the same twist can be obtained using the second leg. Second leg is related to the theta 21 dot, theta 22 dot, theta 23 dot. Okay, it is called as a theta 2 dot here. Okay, let's find out the square axis. Square axis of the second leg. Okay, the linear displacement will be denoted by the theta 22. Okay, so the rotation of this one will make the square axis. Okay, the first element will be the 1 because this is rotational movement. Okay, this rotation will make this kind of motion. So it is dependent on the x direction. So the magnitude of this part is the magnitude is the a2. Okay, and 0. Like this, we can find out first the square axis of the second leg. Okay, how about the second, this one? Theta 22. Okay, this movement can be associated with the square axis of the second joint. So there is no rotation movement. It is corresponding to the minus y. So 0 and minus 1. Because the linear movement should be normalized as a unit vector if there is no rotation movement. That is the definition of a square axis. How about the third one? Okay, this rotation movement. So we should add the 1 here, and this rotation movement will make the x directional movement. So this part is the a magnitude of a minus theta 22. So a2 magnitude minus theta 22. There is no y. This will be the 0. Okay, it must be the J2 and J3. J3 is about the third leg. Theta 31 dot, theta 32 dot, theta 33 dot. Okay. Okay, here theta 11 dot, theta 31 dot, 31 dot will make the rotational movement. So 1, and the square axis will move the minus y direction. So 0 and minus a3, magnitude of the a3. Is it right? The second joint is the theta 32. This will be the linear movement, so rotation part will be the 0 and 1, 0. Okay. And the third joint, this rotational movement, theta 33 dot, will make this kind of linear movement. So rotation part will be the 1. Okay, so x part will be theta 32 will be dependent on this part. So theta 32 will be here because this is the theta 32, and minus y. This will be the square axis in the y direction, minus y. So minus a3. Okay. Like this, we can find out the 3 Jacobian. J1, J2, and J3. Okay, let's make this H matrix. H matrix will be the 1, 0, A1, 0, 0, 1, 1, theta 1, 2, A1 magnitude. Okay, the minus 1 minus A2 0 and 0 0 1 and the minus 1 minus A2 negative of the minus A2 plus theta 2 2 and 0 and 3 by 3 zeros should be added to match the matrix. So 3 by 3 0. Okay, one more 3 by 3 zeros and minus J2, so same one, minus 1 minus A2 0 0 0 1 minus 1 minus A2 plus theta 2 2. Okay, and 0. This last part will be the J3. So 1 0 minus A3 0 1 0 1 theta 3 2 minus A3. Okay, like this we can find out the 6 times 9 Jacobian. The latter part will be the theta 1 1 dot, theta 1 2 dot, theta 1 3 dot, theta 2 1 dot, theta 2 2 dot, theta 2 3 dot, one more theta 3 1 dot, theta 3 2 dot, theta 3 3 dot. Okay, here this mechanism has the 3 active joint where the prismatic joint must be the active. So active, active, and active. Is it right? The corresponding column vector active, this column active, column, I'm sorry that this is not active, active and active. Let's collect the active part. Okay, so H can be rearranged. Active part, this is the active 0 0 1 0 0 0. Active here, one more. Okay, 0 0 1 0 0 1. Okay, this is the active 0 0 0 0 1 0. Okay, and then the 3 active joints should be added. Theta 1 2 dot, theta 2 2 dot, theta 3 2 dot. Okay, it will be denoted by the QA dot, active joint angle. And the remaining 6 column vectors will be the passive Jacobian. The first one 1 0 A1 0 0 0. The second one will be the third column of H matrix 1 theta 1 2 A1 0 0 0. Okay, the first column will be added here minus 1 minus A2 0 minus 1 minus A2 0. Okay, the sixth column here minus 1. Okay, okay, like this we can collect the 6 column vectors. It will be corresponding to the theta 1 1 dot, theta 3 1 dot, 1 3 dot, blah blah, theta 3 3 dot, 6 element. Okay, from here and here. Okay, so the H matrix can be written HAQA dot plus HP QP dot will be the 0. Okay, let's denote this 6th element as a QP dot because it is passive joint and there are no actuator in the QP. So HP has the full length. It belongs to 6 times 6 real space. So QP dot can be obtained minus HP inverse HA QA dot. If you know the QA dot, then using this matrix, we can find out the passive joint angle velocity. Okay, so it is related to the passive Jacobian. Okay. Okay, there is no blank here, so this 6 by 6 matrix should be full length in order to avoid actually the singularity. But okay, after making the 6 by 6 matrix, then you can check the length. Actually, it loses length. It means there is no HP. It is corresponding to the actuator singularity. Okay. In order to avoid the actual singularity, we should replace or change the actuator joint, such as this prismatic joint can be prismatic actuator can be replaced with the joining the rotary actuators. Like this, you can exchange the active joint to another one. Then the actuator singularity can be avoided. Okay. Okay, it's not easy. Anyway, we can find out how to solve the singularity problem and the inverse kinematics and the pole kinematics. Okay, let's move to the next issue. Okay, it's not difficult. Exercise 7.3 is how to solve the inverse kinematics, and then we should count the number of the inverse kinematic solutions. Okay. In here, we will assume that all the link has the same link length in this configuration. Okay. Okay. As mentioned before, the IK inverse kinematic issue is about for given P and R, we should find out the theta 1, theta 2, and the theta 3. Okay. If you give the prismatic, P vector and the rotation matrix of the body plane, then we can calculate theta 1 angle here, theta 2 angle, and theta 3 angle. Okay. It's not difficult in the case of the parallel mechanism, such as closed loop system. Okay, let's make the equation about the post leg. This is the A1. Okay, let's denote this vector as a D1. And then the P vector is here, and then the B1. Both two loops should be equal each other. So the A1 vector plus D1 vector will be equal to P plus B1, but B1 is denoted, is expressed in the body frame, so rotation matrix should be multiplied in advance. So B1. Okay. A is given, P is given, and B1 is given, R is given. Only we don't know the D1 vector. Okay. Okay, so D1 square, if you generalize this equation using the index I, Di square will be the P plus rotation Bi minus Ai transpose P plus RBI minus AI. Okay, the square value of the T will be the magnitude as a scalar, so we can write down the transpose operation of the same vector. Okay, this is the standard procedure to solve the inverse kinematics. Okay, it's not difficult, so let's consider. We can find out D1, magnitude of D1, very easy way. So this is the D1. Okay, maybe the magnitude. Let's consider this triangle. This is the L, because all the link are same as a L. And then this is theta 1, so this is the theta 1, theta I, for the general, without loss of generality. This part will be the pi minus theta I. This length will be the di magnitude. Let's apply the law of cosine. Okay, law of cosine will bring a very simple equation. Okay, di square will be equal to L square plus L square minus 2 times L square. This angle should be multiplied using the cosine. Cosine pi minus theta I. Okay, cosine pi minus theta I is equal to minus cosine theta I. So di square is equal to 2 times L square plus 2 times L square cosine theta I. It can be applied to here. So 2 times L square 1 plus cosine theta I is equal to P plus RPI minus AI transpose P plus RPI minus AI. Okay, right hand side, we know the right hand side, okay, because the for the IK problem P are given and B and A is dependent on the mechanism as a constant vector. Okay, so we know that the right hand side. So cosine theta I can be find out like this: 2 times L. If you denote this value as the di square, magnitude of di square, and then minus 1 is required to find out the cosine theta I. So theta I is equal to arc cosine 2L times minus di square minus 1. Okay. Okay, the arc cosine will provide the two solution for the theta I. It means it has the two kinds of leg structure. First one and the second one. Okay, so it provides the theta 1. We have the two theta 1. How about the theta 2? It has 2 times 2 times 2 because it has a 3 leg. So a solution will be possible. Okay, like this. This is the first solution. This is the second solution. Okay, like this we can find out the 8 kinds of leg structure, leg statures for the inverse kinematics. Okay, maybe it's not difficult. You can understand easily. Okay, let's move to the next issue. Okay, exercise 7.4. Find inverse kinematics and the pole kinematic Jacobian JA from the twist of the S as a JA QA dot. QA dot implies the actuated joint. In here, actually in the textbook there are 2 kinds of actuation set, but I will consider only one, such as the theta 1 dot, theta 2 dot, and the psi 1 dot will be chosen as an actuator. The remaining 3 joint will be chosen as a passive joint without actuator. Okay. This computation provides the numerical data. This is the space frame. This is the body frame. So A1 vectors here. A1 vector will be the 1 plus 1 plus 1. So 3, 0. And then A2. This is the A2. A2 will be the 1 plus 1 plus 1 plus 1 plus 1. So in the x direction we have 4. How about the y? 1 plus 1 plus 1 plus, so 3. Like this, the A1 and the A2 are stationary vector. Okay. how about the B1 and the B2? From here, B1, this is the B1, so 1 and minus 1, like this, and the 1 and the plus 1, like this, in the body frame. Okay, using these two constant vector, we will derive the inverse kinematics and for the kinematic Jacobian. Okay, let's consider. Let's consider A, B, C leg. This leg. Okay, here A1 vector plus D1 will be equal to P plus B. P plus rotation matrix function of the pi and B1. Okay. Okay, let's write down this equation in detail. A1, as you know, the A1 will be the 3, 0. And the D1, okay? D1 is dependent on the theta 1 and the theta 2. Theta 1 and the, okay, let's describe it in more detail. Okay, this is the theta 1 and this is the theta 2. Okay, like this, D1 vector, this leg length is the unit as a 1, so the cosine theta 1 plus cosine theta 1 plus theta 2, okay, to denote the x direction of this vector. Sine theta 1 plus sine theta 1 plus theta 2. Okay, like this we can express the D1 vector. This will be equal to P. P will be the Px and the Py. Maybe the Px is 1 and 3. Is it right? But for the generality, we will denote the alphabetic variable instead of the numerical value, okay, Px and the Py, okay? And rotation matrix will be the cosine pi minus sine pi, and the cosine pi. And then P1 is equal to 1 and the minus 1. Okay, like this, theta 1 plus theta 2 plus theta 3 will be equal to pi. Okay, is it right? Theta 3, this is the link 3, and maybe in this case the 0 value. This is the theta 3. Okay. One more. Actually, it provides the 3 equation using the 3 unknown, theta 1 and the theta 2 and the theta 3, but we have 3 equations. First, second, and third. It must be the nonlinear equation, but we can solve it using the property of the sine and cosine. Okay, on the other hand, DEF leg. Maybe the similar procedure can be applied to here. Then we have 3 equations and 3 unknown, such as psi 1, psi 2, and psi 3. Okay, using the similar procedure. Okay, like this, we have 6 equations and 6 unknown. After tedious manipulation, algebraic manipulation, we can find out the 6 unknown variable for the inverse kinematics. It's not difficult because the sine and cosine has the many provides properties. Okay, let's move to the Ford kinematics Jacobian, JA. Okay, this is the main issue of this computation. Okay, I will delete the inverse kinematics procedure. because the forward kinematic Jacobian is a little bit difficult to understand. Anyway, I will try to solve it as easy as possible. Okay, ready. Okay. As shown in the exercise 7.1, we have provide the twist equation. For this computation, we have two twist equations, such as the twists S will be equal to J1 theta 1 dot. Theta 1 dot is composed of three elements, theta 1 dot, theta 2 dot, and theta 3 dot. I'm sorry, this is the theta dot. To avoid the confusion of notation. Okay, theta dot. And it will be equal to J2 psi dot. As mentioned before, psi dot will have the three elements, psi 1, psi 2, and psi 3. So J1 and J2 has the 3 by 3 matrix. Okay, let's find out the J1. It's not difficult because the J1 can be found out using the square axis concept. Okay, J1 and theta 1 dot, theta 2 dot, theta 3 dot. Okay, theta 1 dot is applied to here, theta 1 dot. So the first element will be the 1, is it right? Because the first element with omega z and Vx and Vy. Okay, to denote the twist. Okay, unit rotational velocity will be added to express the square axis. At that time, minus y direction linear movement will appear. Okay, so the length will be the 3 here. So 0, minus 3. Okay. The second column is related to the theta 2 dot. Okay, theta 2 dot here will be chosen as a 1. I'm sorry, this is the 1. Okay, the 1, and then the same, the minus y directional linear movement will appear. So 0, minus 2, because this is a 2 by adding a 2 element. Third column will be related to this one. Okay, theta 3 dot as a 1 will make a linear movement like this. So x directional linear movement is related to the 1. So 1 and minus y minus 2. Like this we can make the J1 matrix. Okay, on the other hand, J2 is related to the psi 1 dot, psi 2 dot, psi 3 dot. Okay, psi 1 dot moved like this at that time. Okay, psi 1 dot as a 1. This rotational movement will make some linear movement at the space frame. Okay, so it can be decomposed xn minus y. X directional linear movement will be related to the 1, 2, 3. So 3. How about y? Y will be related to the 1, 2, 3, 4. Is it right? Minus y, so minus 4. The second column is related to this one. Okay, maybe this vector will make the linear movement here. 1 and 3 minus 3. Okay, here theta 3 dot will make the linear movement like this. 1 and x is the same, y is the minus 2. Like this we can find out the Jacobian matrix J1 and the J2. Okay, from the open chain concept. Okay, then let's make the big matrix using the two Jacobian, okay, such as J1 theta 1 dot minus J2 psi dot will be the 0. It can be denoted by the H matrix, and then Q vector will be the 0. Okay, let's make the H matrix. H matrix will be the J1 element first here, 1, 0, minus 3, 1, 0, minus 2, 1, 1, minus 2. And then minus J2 appear later part, minus 1, minus 3, 4, minus 1, minus 3, 3, minus 1, minus 3, 2. And then the sixth element should be appear here, theta 1 dot, theta 2 dot, theta 3 dot, psi 1 dot, psi 2 dot, psi 3 dot. The resultant, the matrix vector multiplication will be the 0, 0, 0, 0. Okay, from this equation, HQ dot as a 0, let's choose the active joint. Active joint is defined theta 1 dot and theta 2 dot and psi 1 dot. This is the active, this is the active, and this is the active. So QA dot will be defined theta 1 dot, theta 2 dot, psi 1 dot. The corresponding column vector, this column vector, and the column vector will make the active Jacobian. Okay, so we can decompose this equation. 1, 0, minus 3, 1, 0, minus 2, minus 1, minus 3, 4. And then theta 1 dot, theta 2 dot, psi 1 dot as a QA dot. The remaining, the passive joint, this is the passive, and passive. So 1, 1, minus 2, minus 1, minus 3, minus 3, minus 1, minus 3, and 2. And then the passive joint angle, theta 3 dot, psi 2 dot, psi 3 dot will be the 0, 0, 0, 0. Okay? Let's denote the first matrix as a HA. This is the QA dot plus HP and QP dot will be the 0 vector. So the QP dot can be found out minus HP inverse HA QA dot. Okay, if you define QA dot, then we should calculate the QP dot using this equation. Okay, this can be denoted as a JP because it produces the passive joint angle. So JP QA dot. Actually, this matrix inverse and multiplication will be equal to minus 1.5, minus 1.5, 0, 1, 0, 2, minus 1.5, minus 0.5, 1. Okay, and then QA dot. Okay, like this we can find out some relationship between the passive joint and the active joint. Okay, let's come back to the twist Jacobian. You get twist here. I'd like to this equation using the only active joint. It means JA and QA dot. Is it right? Okay, it is equal to J1 theta dot from here. Okay. Okay, theta dot. Okay, the J1 and theta 1 dot, theta 2 dot, and the theta 3 dot. But theta 3 is the passive. Okay, so we will, the result will be this equation will be the theta 3 dot, psi 1 dot, psi 2 dot, psi 3 dot. So first law will be corresponding to the theta 3 dot. So we will make the another matrix J1 and element will be changed. Theta 1 dot, this is the same, theta 2 dot and psi 1 dot. So theta 1 dot is equal to theta 1 dot, it implies the 1, 0, 0. Theta 2 dot is the same, so 0, 1, 0. Theta 3 dot should be expressed using the QA dot. So this element should be added here. So minus 1.5, minus 1.5 and 0. Okay, so J1, we know the J1 and the latter equation by multiplying both matrix 1 and 2, then we have minus 0.5, minus 0.5, 0, and 1.5, minus 1.5, 0, 0, 1, 0, and then QA dot. So this matrix will denote the JA. So we find out the JA matrix from this relation. Okay, like this we can find out the active Jacobian using the column exchange or column extraction from the pool or matrix H. Okay, I think it's not difficult. It is related to the row operation or column operation of linear algebra. So I'd like to recommend you to solve the 7.8 and the 7.7. Actually 7.7 is related to the delta robot. Delta robot does not change the orientation of the ND vector. So rotation matrix is the identity. The remaining issue is very similar with the 7.3. So after reading the problem statement, then you can solve 7.7 and 7.8. If you have some difficulty in solving those issues,